Right now, the Akashi-Kakyo Bridge in Japan is moving. Not swaying dramatically, just breathing, expanding and contracting with the temperature. On a hot summer day, the main span alone stretches almost 3 feet longer than it does in winter. 3 feet? On a bridge, most people, if you asked them, would say suspension bridges hold themselves up with cables. Big, thick steel cables stretched across towers, holding the deck up like a hammock. That's what it looks like from the road, from the water, from every photograph you've ever seen. And that answer is not wrong. It's just about 1/10 of the actual story. Because what nobody tells you, what the engineers almost never mention in public, is that the cables are only half the system. The other half is buried, anchored, hidden inside massive concrete blocks that most pedestrians walk right past without a second thought. Some of those blocks weigh more than 250,000 tons. They don't move. They never move. And that is precisely what makes the whole bridge possible. By the end of this video, you will understand why a suspension bridge isn't really suspended at all, and why the most important structural element in some of the world's largest bridges is something you can't see from the outside. The first explanation most people reach for is tension. The cables are under tension, they pull, and the deck hangs from them. Simple enough. And the physics isn't wrong. The main cables of the Golden Gate Bridge, for example, carry roughly 200 million pounds of force, each one. So tension is real, and tension is massive. But tension in what direction? That's where the obvious answer starts to dissolve. A cable stretched between two towers isn't just pulling down, it's pulling outward, sideways, diagonally. Cables on a suspension bridge want to straighten out. They're always fighting the curve that gravity forces on them, and that means they're constantly trying to drag the towers toward each other and yank the anchors on each shore outward and upward. The tension isn't just holding the deck. It's doing something much more violent than that. So the second explanation arrives: the towers. Big, heavy towers resist the inward pull of the cables. The towers of the Verrazano Narrows Bridge in New York are taller than the Chrysler Building. They weigh more than 27,000 tons each. Surely those towers are what's doing the work. And again, yes, partially. The towers carry vertical loads. But towers are not anchored horizontally. They sit on foundations that allow rotation. The towers are not what's stopping the cables from pulling the entire bridge inward and down. Something else is dot. This leads most people to a third idea. The deck itself acts like a beam. The road surface, the trusses underneath it, the whole rigid platform, maybe it's stiff enough to push back against the tension, like a bow and arrow held in balance. Some bridges do work this way. Certain cable-stayed bridges use their decks as compression members. But true suspension bridges, the Brooklyn Bridge, the George Washington Bridge, the Humber Bridge in England, their decks are not rigid in that way. They flex, they move. They are not the counterforce. So what is? Here's where you need to change the mental image you're working with. Stop imagining a bridge as something that hangs. Start imagining it as something that pulls. The cables of a suspension bridge are not just holding the deck up. They are pulling with tremendous force on 2 points at either end of the bridge. Those points are called the anchorages. And everything that makes a suspension bridge stable comes down to what happens at those anchorages. Think of it this way. Tie a rope between two trees, hang a heavy bag in the middle. The rope pulls on the trees, pulls them inward, tries to drag them together. Now imagine those trees could move. The whole system collapses. A suspension bridge is exactly that situation, but the scale is almost impossible to comprehend. The main cables of the Humber Bridge, when fully loaded, pull on their anchorages with a force equivalent to roughly 40,000 tons at each end, not pushing, pulling, trying to drag those anchor points outward, toward the bridge and upward out of the ground. So how do you resist a 40,000-ton pull? You bury something heavier. The anchorage of a suspension bridge is not just a bolt in the ground. It's an engineered mass, a gravity anchor designed to be so heavy that no cable tension can move it. The anchorages of the George Washington Bridge in New York are concrete and steel structures that weigh approximately 350,000 tons each. For reference, that is heavier than every aircraft carrier the United States has ever built. Combined, sitting on a single site, doing nothing except not moving, and not moving is the entire job. The anchorage wins through sheer stubborn mass. But here's what makes this more interesting than it first appears. The anchorage isn't just a pile of weight dropped on the ground. The cables don't just attach to the surface of the anchor block. They go through it. Inside every major suspension bridge anchorage, the main cables are unwound, spread apart, strand by strand, and threaded through a structure called the anchor chamber. Those strands fan out like the roots of a tree, distributing the cable's tension across hundreds of separate anchor points embedded deep within the concrete mass. The load doesn't stay at the surface. It goes into the heart of the block, where it is distributed across such a wide area that no single point is ever overspread. The anchorage doesn't just resist the cable, it dissolves the cable's force into itself. Now ask a different question. What if you can't bury 350,000 tons of concrete? Sometimes the ground won't allow it. Sometimes the geography won't allow it. Sometimes the budget won't allow it. And this is where the counterweight system gets even more inventive, because engineers don't always use mass. Sometimes they use the rock itself, at the Clifton Suspension Bridge in Bristol. England opened in 1864, still in use today. The anchorages are not gravity blocks at all. They are tunnels. The cables are threaded into the limestone cliffs on either side of the Avon Gorge, attached to iron plates buried deep in the rock. The cliff itself becomes the anchor. The bridge borrows its stability from geology, from hundreds of millions of years of compression that turns sediment into stone. It is, in the most literal sense, held in place by the earth. But even that isn't the whole story. Because a suspension bridge doesn't just need to resist static loads, it needs to resist loads that change wind, traffic, temperature, and a static anchor block, no matter how heavy, cannot respond to a bridge that's breathing. This is where stiffening systems enter the picture, and where the hidden engineering becomes almost musical in its complexity. Every suspension bridge that carries vehicular traffic incorporates a system for distributing moving loads across the entire span, not just the point where a heavy truck happens to be, the deck's stiffening trusses, the backstay cables, the angle at which the cables meet the tower saddles. All of these are tuned the way a piano is tuned. Each element has a designed flexibility and a designed resistance, and they interact with each other in ways that take months of computer simulation to model and decades of observation to fully verify. On the Tacoma Narrows Bridge in Washington, the original one, Galloping Gertie, which collapsed spectacularly in 1940, the stiffening system was too shallow, too elegant, too light. The deck was only 8 feet deep, held up by solid plate girders instead of open trusses. When the wind hit it, the bridge didn't just sway, it resonated. The wind found the bridge's natural frequency and matched it, pumping energy into the oscillation until the structure tore itself apart. The anchorages held, the towers held, the cables held. What failed was the tuning. The replacement bridge, opened in 1950, has a stiffening truss 25 feet deep. You can see the difference from the water. It looks heavier, less graceful, more utilitarian. It has never galloped once. This raises a question that most people don't think to ask. How does an engineer decide how much stiffness is enough? How much anchorage weight is enough? How much flexibility is too much? The answer is a concept called the cable-sag ratio. The ratio of how low the main cable hangs in the middle compared to the distance between the two towers, and this single ratio controls almost everything else about the bridge. A shallow cable, one that barely sags at all, stretched almost flat, seems like it would be strong. But physics disagrees. A shallow cable carries its load with enormous tension. The forces at the anchorages are massive. The towers need to be stronger. Everything costs more, and the bridge becomes dangerously sensitive to uneven loading. A deep cable, one that sags significantly, forming a pronounced curve, carries its load with less tension. The anchorage forces are lower, but the towers need to be taller to keep the curve from lowering the road surface, and a deep cable is more sensitive to wind. The bridge can undulate. The optimal sag ratio for most major suspension bridges is around 1/10. For every 10 feet of horizontal span, the cable sags 1 foot at its deepest point. The Golden Gate Bridge uses almost exactly this ratio. So does the Humber Bridge. So does the Akashi. Not because engineers copied each other, but because the physics leads everyone to the same answer. 1/10 is where the forces balance, where the anchorage demands are manageable, where the wind sensitivity is acceptable. It is a number, The geometry of the problem generates on its own. Here is what changes when you understand. This dot, every suspension bridge you've ever crossed has been a negotiation between the cable tension pulling outward and the mass of an anchor block pulling back, or the strength of bedrock holding firm. The road you drove on, the view you had, the gentle flex you felt under your feet, all of it was made possible by something you never saw, something buried, something that has been silently resisting forces that would flatten a city block. The Brooklyn Bridge, when it opened in 1883, was the longest suspension bridge in the world. Its anchorages, 2 on the Brooklyn side, 2 on the Manhattan side, are still there. They are massive granite and limestone structures, each one the size of a city block, each one descended 50 feet into the ground. They have been resisting the pull of those cables for over 140 years, and in that time, they have moved by the best measurements available, essentially zero. What this means for modern engineering is equally striking. As spans get longer, and they are getting longer, with proposed crossings in Italy, India, and the Strait of Gibraltar that would dwarf everything built so far, the anchorage problem becomes the central problem. You can design a cable. You can design a tower. The thing you cannot easily engineer is the ground. The Earth has to cooperate. If the geology beneath an anchorage site is wrong, if the rock is fractured, if the soil is unstable, if the water table creates pressure, the entire bridge becomes unbuildable, not because the span is too long, but because there is nowhere to hold on. The most ambitious crossing, currently proposed, a bridge across the Strait of Messina, between mainland Italy and Sicily, has been debated for decades. Not primarily because of the main span, but because of what lies beneath the anchorage zones. The seabed there is complex, the seismic risk is real, and the anchor block demands for a 3.3-kilometer span are almost beyond current construction technology. The bridge's viability comes down, ultimately, to 2 questions. Is there enough rock on the Calabrian shore, and is there enough rock on the Sicilian shore to hold on to? The cables want to fly. The anchorages are what say no. There's one more thing worth knowing before you close this video. Something that changes the way you'll look at bridges for the rest of your life. The cables of a suspension bridge are not static objects. They move. Every day, as temperature rises and falls, they expand and contract. As traffic loads shift, they deflect. As wind changes direction, they flex in ways that are almost invisible to the human eye, but are measured constantly by sensors embedded throughout modern bridges. The Golden Gate Bridge has over 600 permanent sensors. The Humber Bridge monitors wind, temperature, load, and structural vibration in real time, all day, every day. And the anchorages don't move, not by a measurable amount, not in temperature, not in wind, not under full traffic load. They are the ones still point in a structure that is always subtly in motion. A bridge is not a static object. It's a dynamic system that has been designed to look still. The anchorage is how that illusion is maintained. It is the fixed point around which everything else is allowed to move. The buried counterweight that absorbs every oscillation, every load shift, every thermal breath of the structure above it, and converts all of that energy into nothing more than a slight, imperceptible compression of the concrete and rock below. If you want to understand why this matters beyond bridges, why the concept of a hidden counterweight, a buried anchor, an invisible resistance, shows up in everything from earthquake-resistant buildings to the moorings of offshore oil platforms to the foundations of the world's tallest skyscrapers, that's a thread worth pulling, and it goes much further than you'd expect. If that's the kind of question you can't stop thinking about, Discovery Loom is where questions like this live. Subscribe, and we'll keep pulling the thread together.